Hello and welcome back to Calculus 1, section 4.5 on optimization. Yes, problems, yes. We are going to do the word problems regarding the min and max calculations. In general, we are interested in maximum profit, minimum cost, let's say maximum volume of the box so you can put as much stuff as possible. Maybe you want to minimize the surface area. So there are a lot of optimization problems, or maximize the area for that matter. So there are a lot of optimization problems that we can work on, and some of the best we're going to outline in class, but guys, there is such a big variety for you to practice and enjoy at home. These are the problems that you will see in engineering. They will be upgraded heavily for your later courses in engineering and so, you know, take a look at the section and try to understand the most you can, because this is what makes money, this section. So let's talk about the idea first. Say you are, again, this is just to show off the method. It's not something that you would particularly be paid to do. Find two numbers, x and y, such that their sum is, let's say, and you say, you know what, I'm not going to do any heavy-duty math over here, I'm just going to guess. Okay, fine, let's go. 0 plus 18 is 18, right? So 0 times 18 gives you 0. 1 plus 17 is also 18, but then 1 times 17 is 17. Well, that's better. 2 plus 16 is also 18. 2 times 16 is very good.
I think the goal
so it's better one, right?
Two values that are the closest together, right?
Well, we'll see. So 3 plus 15 is 18. So 3 times 15 is 45. So you can see that as you are trying to get two numbers, the product keeps rising, right? So this is 56. So we went from 0 now to 56, and then we have 5 plus 13 is also 18, and then 5 times 13 is 65. 65. And then 6 plus 12 is also 18. 6 times 12 is 72. 7 plus 11 is also 18. 7 times 11 is 77. You see, it gets, the product keeps getting larger and larger as we are doing this. So 10 plus n is 18. 8 times 10 is 80. And then we have 9 plus 9 is also 18. 9 times 9 is 81. And then you go, oh, 10 plus 8 is also 18, but I already had that situation. And it's, as you said, going downhill now, 80, so it looks like we got it. So it has to be 9 and 9 in this case. It's not always going to be two same numbers, but in this particular case was 9 and 9. Well, this was terribly inefficient.
Yes.
It took a long time, and what if someone says, well, numbers add to 243, what's the maximum, right? In that case, you say, oh. So you have to go and, compute all the way. So is there a way to do this better? And the answer is obviously yes, since we have the section. So if you read up there, you say find two numbers. So they're clearly interested in x and a y. So in this case, x equals 9, x equals y equals 9. So find two numbers x and y. So their sum is 18. I can transfer that into mathematical equation x plus y equals 18. Because we are looking for a number x and the number y. So when we add them, we get 18. And we want their product to be a maximum. So that's xy equals a max. So this part is called modeling. When you take the word problem and you transfer that word problem into mathematical sentences, which we call equations. So it's like translating English into math. So once I'm done with that, I need to write some terminology here. So this equation is called the constraint. And this equation is called objective. Equation, I can put equation both. Constraint equation and objective equation. You see, your objective says that multiplication of two numbers needs to be maximum. Well, can I just say 100 times 100, right? That's going to be bigger than 81. But it has to be under constraint that the numbers add to 18. Well, 100 plus 100 is not 18, so it's disqualified. So we have always the objective equation, which is the equation, the concept that we are trying to minimize or maximize. And then there is a constraint equation, which is there to give us some condition that has to be fulfilled. And you will always be able to find two of these equations in your word problem. Now, a lot of students usually ask, so how do I know which problem is optimization, which problem is differentials, which word problem is differentials, and which word problem is related rates? Well, this one doesn't mention rates at all, right? It's mentioning minimum and maximum values. So when you read, you will be able to tell the difference, right, if you pay attention. So our problem up there had these two things going on. The sum of the two numbers that are unknown needs to be 18, and the second one, the product of those two numbers, needs to be the maximum number possible. Once you are able to write those two equations looking at the word problem, the next step is to combine these two equations into a single equation and then hit it with the derivative. Now, why are we combining these two equations? To kill one of the variables. If you look at this system, it has three variables. There is the x, y, and you also don't know what the maximum is. They didn't tell you that the maximum is 81 in the problem. We discovered that by trial and error, right? So you have three variables, and you will always have more variables than what you have information in the problem. So what you need to do is to involve the derivative. Now let's see. The process goes like this. From the constraint equation, you solve for one of the variables. So you will go into constraint equation and you will solve for one of the variables. And then you will plug that in into this equation, and you will get x times 18 minus x equals a max. So that's 18x minus x squared equals a max. And now you have an equation which would be the one variable model. So this is a one variable model. And now, once you are there, you hit this with the derivative because you are maximizing. And you know that when you are looking for a maximum, you are supposed to take the derivative and set equal to 0, right? Well, when you take the derivative here, you will get 18 minus 2x. And remember that the maximum, the derivative of that is 0. Because what's maximum? We already know, it's 81, right? It's some kind of number. It's a constant, exactly. So maximum is a constant. Maximum volume of 100 inches cubed. Or maximum surface area of 2 square miles, right? It doesn't matter what the number, it's a constant of some kind. And when you take the derivative of that, you still don't know what it is, but you know that it's a number, and derivative of that is equal to 0. So now you get to actually see that as you do these word problems, you have derivative equal to 0. Well, that's what you learned in 4.1. The way to find maximum was to take the derivative, set it equal to 0 to find the critical point. And then min and max was at the critical point. So now you are going to find your critical point by simply solving this equation, and you see x equals 9. Right? You see immediately x equals 9. Then we know y equals 18 minus x, which is 18 minus 9. It's another 9. So x equals y equals 9. And we solve the problem using calculus rather than trial and error. Because as I said, right, we might want to add to 200 and something rather than 218. You don't want to sit and check all of the values. So that's our goal. And now we want to apply this to situations in engineer, as you would say, in the real life, because this over here is fake life, right? Is it? It's fake? It's fake, exactly. Fake life. All right, let's go to real life. How about some farmer problems? So let's take a look at the challenge where farmer has, let's say, 2,000 yard of fence, rectangular plot of maximum area. This is one of the most popular problems, and we are going to see a lot of modifications to this. So just like your related rates, you first ask yourself, what's the geometry, right? Because the word rectangle is mentioned. Common sense is, let's use the rectangle, right? So farmer wants a rectangular plot of land. And what does this black line represent here? The perimeter. And what do you put on a perimeter in a case of the farmer? That's where the fence goes. It's called the perimeter fence. It's going to fence off the area that is inside. So I have my x and my y values. And who can tell me the constraint equation? X plus y equals 1,000 will cover this much. 2x plus 2y, excellent. 2x plus 2y equals 2,000. That is our constraint, because that's all the fence you have. Right? If you want more, you gotta go buy more. Constraint. We will, and it will be equal to 1,000. Is that what you said?
That's what I said. I was like,
You said x plus y equal 1,000?
yeah, in my head I did it by 2.
Yes, that's just, I'm a terrible person.
Okay.
So you should support.
No, that she was right.
She was right.
Okay.
You see, this is so now you're learning to deal with terrible people. And yeah, so you were 100% right in what you said.
Okay.
It will take me an extra step to get there. What is the second equation? What is the objective equation? What am I supposed to do? Yes. Excellent. So xy equals a max. Now look at these two equations. Is this in any way different than a previous calculation? Absolutely not. Right? We are going to go with x plus y equals 1000 and xy equals a max. And you are supposed to follow exact steps from the previous problem to calculate the values for x and a y. So go.
Yeah, this is the same exact thing before, the text structure with different values. What would you say is the difference between how you define an objective equation and the constraint equation?
Objective equation is the one that has min or a max in it. Because that's what you're looking for, right? You are looking to maximize the area. You're looking for maximum area in this case. So objective equation has to contain that max.
Yeah. And then the constraint equation, that just has the number you're solving for?
Mm-hmm. The constraint has both of them. Both numbers that you're looking for.
Numbers.
So did we all get that x equals y equals 500, so it's a square?
What?
Yes.
Yeah, I got 500.
So we have a square. Now we are going to modify this little bit because we are going to have a river over here. Yay! So now farmer doesn't have to fence off everything. He can fence off 3 of the sides. Are you expecting to get larger or smaller area now?
Larger area.
Larger area.
More space for you.
So try to write you still have 2,000 yard fence. The answer is what?
Oh, no, I was just saying he has more fence, that's why I get bigger. Or he doesn't have to use it.
Yeah, doesn't have to fence one side. So, okay, let's see. It's the same problem again, it's just a little bit different numbers. Let's see what you get. So do we all have x plus 2y equals 2,000?
Yes.
And we still have xy is max.
Yes.
Great. So now x is equal to 2,000 minus 2y. So that's 2,000 minus 2y times y equals, it will be 2,000 y. I said let's do it in terms of y because it's avoiding fractions. So now dy and 4. Yes, but your x is now different, right? X is 2,000 minus 2 times 500, which is 1,000. So the new dimensions are 1,000 by 500 yard. The old dimensions were 500 by 500. This is actually twice the area. We did not fence one side and we got twice the area. Cool, huh? How about if we need to put some bins in it? Let's say you want to separate stuff.
Well, I have to take away from the overall area.
Cabbage, rabbits, and tigers. You can't put them together. I don't know what happens to rabbits. You put them together with tigers?
I don't. It's just like,
Well, you didn't read the book. Apparently nothing happens. They had them on a boat at one point in time. Anyway. So,
it's still 2,000 yards.
yes, still 2,000 yards of fence. So what do you do here? To label this, what do you put? You put 2 X's and 4 Y's. Very good. All right, get busy. You have to account for every single black line because each of those lines is a length of where the fence goes.
Return to find the area of these pens individually.
Well, you just need to find X and a Y, and then we can.
Divide that by 3.
Yes, because the leftover fence. Because see, the trick is that this particular design does not account for you actually having the even spacing for each of the, right? Maybe you have just a little bit of cabbage, right? Tigers were in a third bin, right? So let's move the rabbits here. Rabbits don't need a lot of space either.
No.
And we're just going to leave a lot of space for tigers because they're bigger, right?
So that we don't know what the space for each of them is going to be.
Yeah, so that's why we are not labeling these X, X, and X over here because they might be different lengths. We label the entire length over here as X. And then these 2 Y's, that will be a leftover fence that you get to split, right? 2. And then you can put that fence anywhere you want. So we have 2x plus 4y equals to 2,000. That's our constraint. And still xy equal a max as our objective. X plus 2y equal 1,000. X equals 1,000 minus 2y. Right? Will you ever forgive me? So we plug this into the objective equation, and we have 1,000 minus 2y, y equals a max, which is 1,000y minus 2y squared equals a max. So it doesn't matter if you are solving the problem in terms of x first or the y, whatever is convenient, so you can avoid the fractions. I mean, you don't have to avoid the fractions, you can still power through it. It's easier if you don't have to shovel fractions. Hey, we got that y is 250 yard. And then x is going to be 1000 minus 2 times 250, going to be 500 yard. And it seems that it's 500 by 250 yard this time around. There are endless combinations that you can make and enjoy. How about you put the river and then you have bins, or you have the river, let's say, and then you put 1/4 like that, so that this is x over 2 and y over 2, but the whole thing is y and the whole thing is x, right? So you can play these games, and it's just going to be what the equation, right, what the constraint equation, the objective equation is always x times y equals to max, because that's what the problem wants, to maximize the area so that we can have the most of the vegetables or the most of the animals in that area. How fitting. Let's see what else we can do with this stuff. Minimum surface area of a box, maximum volume of the box. Shipping crates. One of the lucrative majors now is packaging engineering. Apparently, they are getting hired before they even graduate right now. A lot of stuff. All of the stuff that we consume is no longer produced here in any way, shape, or form. So it has to be shipped from the other side of the planet, right? You need to make boxes, and you need to make all kinds of things to contain the product, and also to contain, right, the electronics of the product. So packaging engineering is really cool. And if you think about it, you want to create a box that has maximum volume so you can put the most stuff in it, but you also at the same time want to minimize the surface area of the box. Why?
Then you have to use less. You have to put less resources.
Yes,
in that box.
very good.
Area.
If you have the smallest possible area of the box, then you're using less cardboard, right, to make that box. Now you're going to shave probably 2 cents per box. Sounds good. Would you bother? 2 cents per box? Why?
You're gonna make thousands.
Yes, exactly. You're gonna ship 100,000 boxes, 200,000 boxes. What's 200,000 times 2 cents, right? So you definitely want to shave every penny you can, right? And if you are having someone designing the box and actually was able to save 2 pennies or 5 pennies on 10 cents, right, for a box, well, woohoo, times 10,000 boxes, that's a nice chunk of money saved. So let's take a look at the problem, let's say 19, where they say minimum surface area of the box. Find of all boxes with a square base. Now, this is important for you guys because square base will give you, it's a three-dimensional object, and a three-dimensional object should have three-dimensional variables, x, y, and z. But this is single variable calculus, and the derivative can kill only one of them. So you would still have two variables. If you want the non-equal sides, then it's calc 3 actually. So we are constrained here to have a square base. And if you take a look at your project, if you considered your project at all, you read the question, it says square base. So the project question calls you to create out of regular print paper, right? Regular size print paper, cut it down to a square. So you know that the sides, right? Say by 11, right? So you make it 8 by 5 by 5. And then you are supposed to cut out corners so that when you stand up the edges, they create a box with no top. It's a very simple concept. The question is how big of a squares you get to cut out in the corners, right? Because only one particular value that you cut out in the corners will lead to the maximum volume. So that's and then you are supposed to make that box, you are supposed to decorate the box, and you are supposed to bring the box on Thursday next week. So you will do the calculations, you will take the pictures of the process, because no one is going to look at your steps. No one cares about your calculations and things like that. You are selling the product, so you are not submitting calculations. In your text, you will explain the process of making a box, and because you took pictures and imported pictures into the text, it will be clear what steps were taken to create such a box. And then, the edges you can just glue with a little piece of tape or whatever you guys come up with to, get those edges together. So creating the box and then making sure that the box is not all crushed and bent and destroyed by the time you get to because that's your prototype. That is what sells your skill. If you want to ever work, you better have the skill to write the resume, better have the skill to write your letter of intent, and then if you are submitting a project, better be in a pristine condition, because if it's not, well, next person in line, bye, right? That's what requirements in life are. And no one will in life ever give you half a credit or less of a credit. You just get 0. That's very simple, because there is someone who did a better job. So you always have to put 100% of your effort into everything you do, which will be instilled in you once you graduate. Because right now, whatever you do, it's okay. You're in school, so who cares? Right? Late assignments and it's just handy and stuff. Just do anything. It's good. It's cool, right? So you will work on that project problem. Now, these two problems are somewhat similar. Of all boxes with a square base, see, they never said that the top is open, right? So we have to understand that this box that I'm going to have here is going to be closed from all 6 sides. And they say square base, that's XX, and then you are going to have some kind of a height of the box that it's not the same, so we'll call that a Y. And they say that the volume, which in our case is x squared y, is 8 meters cubed. 8 meters cubed. And this is your constraint, because you don't see any min and max in it. Now they're looking for a minimum surface area, right? Minimum surface area. So area needs to be minimum. Now, what is the area of this box? Go on, I'll wait. I want the formula for area. Yes.
Oh, no.
Oh no, yeah, no.
2x squared, very good. We have 2x squared, we have a floor and a ceiling. Both floor and the ceiling of this box are x times x, that's area. Plus 4y squared for 4 walls. 4xy, that's what you said, right? So each one of the walls is x times y. So you have 4 walls, x times y. You have the floor, x times x. You have a ceiling, x times x. And this is supposed to be minimum, and this is your objective. Why not? Good. So now we're going to go into our volume equation, x squared x squared y equals 8, and say that y is equal 8 over x squared, and plug in to kill a y. So I have 2x squared plus 4x times 8 over x squared. That's where the y was. It's a minimum, which is 2x squared plus 32 over x equals a minimum. All right, time to take the derivative. Let's go. Get busy. Need to solve the equation. Need to know what x is. Nice. So the box is 2 by 2 by 2. It's a cube. Box is a cube.
Oh, that would be the side. Cool. How would you tell that from the list?
What happened?
You did say that you said that the length and width would be x, but what about the height? That was y, right?
Yeah, but we calculated that. So it happened like previous case, x equals to y.
All right,
It's possible.
2, that would be, yeah, I got 8 with that.
Okay. So let's take a look at
0. Have a good day.
Take it easy, Professor.
yeah. Shipping crates. So how about we include some of the business decisions in this one to calculate the minimum cost to make a box for shipping. So shipping crates. A square-based box-shaped shipping crate is designed to have a volume of 16 feet cubed.
All right, it's a square.
So it's the same shape as before. We are going to have a square base, so x and x, and then a y on the top.
All right.
So now, when we have this, we are going to take a look at the material cost. So what they want to do is to say they want the cost to be minimum. Cost to make this. And it says material used to make the base costs twice as much as the sides. So base material 2 times sides as terms of cost, right? And then it says the top is half of the size. Top material 1/2 of the sides in terms of cost. Find the minimum cost. So what dimensions of the box, of the crate, which has 16 feet cubed, will give us the minimum cost to make the box? So we're going to first start with doing the same area of each of these, but you can actually draw the wireframe over here for the box. And it has a top. So this is the bottom, this is the top, and these are the 4 sides for the crate. So something like this, when you fold on these lines here, and then you fold this one as well, it will create the box, the crate. So now, what is the cost function? Well, say that cost of 1 square foot of the side is, let's say, C. I don't know, $1, half a dollar, $10, whatever. It's just a C. So cost of 1 foot squared is C. I have my X and Y's everywhere, right? So what is the cost equation that we are supposed to minimize? Well, we have 4 sides, and each one is at the cost, because sides are at cost, and that's xy. So 4cxy, actually, you know what? C times 4xy. So this is the cost to make 4 sides of the crate. C is the cost to make 1 side. You have 4 sides, and because you are doing this by feet squared, then we have the cost to be C times 4 plus 2C is the cost for the bottom, and the bottom has x squared, plus C over 2, half of C, for x squared, which is the top. So that's the cost equation. Oh, sorry, I have cost on the other side. This needs to be minimum. Needs to be minimum. So cost needs to be minimum. I mean, if you want to run business, that's what it is. And that's your objective equation. And then you have your volume equation, which is, again, x squared y equals 8. That's the constraint. Did I say 16? 16 it is. Feet cubed. Feet cubed. So now, let's simplify the cost equation. We can kick out a C. We have 4xy plus, and guys, now you have a 2x squared plus 1/2 x squared. I hope you see that that's 5/2 x squared when you add fractions.
Oh, yes.
And from the volume equation, which is our constraint, y is equal to 16 over x squared. Now it's really cool to immediately realize, right, the cost doesn't depend on, well,
I forget that.
the dimensions do not, wow, I don't even know how to say this. See, the cost could be $1 or $10 or $100. It would not affect the shape of the box per square foot, which is really, really interesting, because I can divide both sides by c and have this min over c, and when I take the derivative it goes to 0. So the cost really doesn't affect the shape of the box. It's actually the 1/2 and twice the side that is what affects it, which is nice. So at this point you can pick to drag the c with you or to leave the c behind. It doesn't matter. Now I'm going to choose to drag it with me, but we can also do the problem with completely ignoring the cost c. This is not the total cost of the whole box. This is the cost of material for 1 square foot. All right, so now we plug this in, we get c 4x 16 over x squared plus 5/2 x squared
How do we get the value for y then?
equals the minimum from the volume equation, which is our constraint. So c,
Oh, yes.
so we have a 64 over x plus 5/2 x squared equals the minimum. And now if I differentiate this, I'm just going to copy the cost, and I have, well, I'll do the x squared term first. So that's going to be 5x minus 64 over x squared equals 0. And now you see the cost dies anyway, because when you divide it into 0, it's done, it's gone. Now this is again cost per square foot. It's a market value. You don't get to affect that one. You can't do anything about that one. It's not you who's making a cardboard. You are buying that and making boxes, right? It's the same thing like the factory that is making these cell phone case is not producing plastic. It's buying plastic at the market value and then it's making the case, right? So we have 5x is equal to 64x squared. 5x cubed is equal to 64. X cubed is equal to 64 over 5. And finally, x equals to cube root of 64 over 5. Now we're going to get a reasonable number. How many decimals should I use in the answer?
2, 4, 3, 5. My math lab wants 4.
1. There we go.
I said 2 because we're calculating cost.
This is the length of the side.
Oh, yeah, you're right.
And your precision that you had was an integer. Your calculation allows for 1 extra decimal. In the end, the cost will be calculated and you will provide up to cents, which is 2 decimal. But for the length of the side over here, I have 2.3 feet for x, and then y is 16 divided by 2.3 squared is 3 feet. So the box needs to be 2.3 by 2.3 by 3 feet to give you the minimum cost on calculating the, minimum cost to make the crate. Now you can go and you can research what the, let's say, cardboard costs, and then you would plug that for C. You have your X and the Y values. You will plug in your X and the Y values and the C value to actually calculate the cost, which is what you produce in your report to your boss.
Sorry, what was that?
If you want to know the cost, you will have to plug in the values into the cost equation to come up with how much money this actually costs. We only calculated the dimensions. Two more problems, and then we are done with this section. They have this problem, they call it optimal garden, and I usually change this because what they have over there, we're actually going to do something better. So what they have is this rectangle in the rectangle situation with 2 meters. 2 meters is my height, so that's how long this is, and then this is 1 meter, obviously half of my height in this case. So we have 2 meters on the sides and 1 meter on each on the top. Now they're talking about the flower garden and blah blah blah. We're going to talk about a pool. All right. So we have pool. There's water inside, hopefully. And then you want to pour a concrete patio around it. So that's something that makes sense to talk about. Now the constraint is that, I'm going to get rid of the water now. The constraint is that this is 30 meters squared. So the pool is to have 30 meters squared surrounded by the border, which is for us going to be the concrete. What dimensions of the pool would minimize the combined area? So what pool dimensions, which is the inner rectangle, what pool dimensions, which is the inner rectangle, would minimize the combined area Now, why do you want to minimize combined area? Yes?
The less area you have to build, the more money you're going to save.
Yeah, how are you saving the money?
It costs money to get tiles.
To get the concrete. Yes, no, the concrete. Because you are looking to minimize the entire area. Minimizing the entire area, right, you have technically saved on the amount of concrete that you are putting around the pool, and that costs money. Good. All right, so let's call the pool dimensions, we are looking for x and a y. We don't know what those are.
You know, they equal 30.
Yes, that's a constraint. Good. So xy equals 30, and that's our constraint, obviously, because there is no min or max in that equation. Now we are trying to minimize the overall area. So what are my dimensions on the outside? How much is this? X plus 4. Very good.
We're trying to find the overall area?
Yes.
Go.
Why is this x plus 4?
For both sides of
The extra, yes. So pool would be between two blue lines here, you have x. And then on each side, you have additional 2 and 2. So when you add 2 plus x plus 2, you get x plus 4. Now, how about on the side? Y plus 2. Very good. Y plus 2, because the side is y in the middle, and then you have a meter up and a meter down. So they are 1 plus 1 is 2. So my constraint equation over here is x plus 4 times y plus 2 needs to be minimum. Sorry, that's objective, not constraint. Objective equation. So the pool, right, the inner rectangle, the pool, that's given as x times y equals 30 meters squared. That's, you can see that on the picture. Now the bigger side, the concrete, right, the big rectangle, that's going to be the dimensions of the pool plus the stretches that you have on each of the sides. So we have x plus 4, and we have not y equals 2, y plus 2.
Right.
So now we solve, say y is equal to 30 over x, and then, yes.
Y equals, I understand. Y.
So, and then we plug in. So we have x plus 4, 30 over x, plus 2, equals a minimum, and then you FOIL. So x times 30 over x is cancelled, so it's 30, plus 2x, plus 120 over x, plus 8, equals a minimum. We differentiate this in respect to x. 30 and 8, they're both constants, they're gone. So 2 minus 120 over x squared is equal to 0. Two is equal to 120 over x squared. Cross multiply 2x squared is 120. X squared is 60. And now when you take square root of both sides, you get positive and negative value, but we ignore the negative because lengths cannot be negative. Square root of 60, 1 decimal precision allowed, 7.7 meters. So the length of the pool is 7.7. These are bad numbers. 7.7 meters is nothing. It's pretty much like 3.5 times my height. That's a very sad length for a pool.
Oh, absolutely.
And then we have y is equal to 30 over x, which is 30 over 7.7. And we get 3.9 meters. So the pool in this case will have dimensions of 7.7 by 3.9 meters. And that would minimize the cost of the concrete that we lay around the pool. That's what we have. What happened?
Does somebody get used to this kind of equation?
Yeah, it's fun. So one more, and then we take the break. Now this next problem is important because this is what the consulting work is, right? So let's have a seashore over here. There's a sea on this side and a shore on this side. You okay with it?
I might have misplaced something up there.
Now, what I'm going to have is oil rig. Let's say that oil rig is 5 miles away. It doesn't matter. 5 miles away from the shore. And then we're going to have a big refinery, factory on the shore. There's going to be the vertical distance of, let's say, 10 miles. Now, let's call these short distances. So you are not going to run a tanker ship between the two locations, right? Because these guys are taking the oil out, needs to go to be refined, and then turns into gasoline and diesel and plastic and everything else we use. So you build a pipeline. Now, the pipeline has different costs if you're building it above ground, underground, or underwater. So we are only going to build above ground for 10 miles and underwater for 5 miles. So say these are just numbers for us to do math. You can go research the real numbers if anyone posts those. Probably they do. So let 1 mile of pipeline cost ground, let's say $250,000.
Very expensive.
That's probably undershooting it a lot. Because if you consider those big power lines, you know, the big power lines that go like that, and they have this and they go big, right? One tower and one set of wires on one side is 100K. Now as you drive, you see them going, so you count 10 of those, $1 million, right? So this $250,000 is probably, for 1 mile of pipe, it's probably underestimated, but that's okay. Underwater, let's go with $500,000. Maybe put $1 million, but $500,000, whatever. It doesn't matter. $500,000. Wait a minute. All of these prices and things, they're just a joke for these companies, but you know, well, let's put them on. So there are two possibilities that we can immediately see. First off, we say, hold on. Going underwater is twice as expensive as going on the ground. So how about we go the least amount underwater? Well, that's the black line. The black pipeline that goes straight up and across. So the black pipeline, we'll call that pipeline 1. Pipeline 1 is going to have the least amount underwater, and the cost for that part of the pipeline should be the smallest. If you look at the blue, everything is underwater, but it's the shortest distance, right? So blue also has its use, right? Maybe. Let's see which one is better. Do we need calculus? No, we don't need calculus. Just multiply by the cost. You have the lengths, you have the cost, just multiply the stuff out and you're done. So let's take a look at the black pipeline. So I have 10 miles at the cost of 250,000 plus 5 miles at the cost of $500,000, which will give me 2.5 mil plus another 2.5 mil is $5 million.
Yep.
So 5 million to build the black path, right? We have 10 miles on the ground, 5 miles underwater, and that's what we have. Now for the blue path, well, for the blue path, I need to actually calculate the length. I don't know the length. So what do I do to find the length? Pythagorean Theorem. So length of the blue path, which is denoted as L over here, is going to be what? 10 squared plus 5 squared, which is square root of 125. Great. Now we're going to hit that to 1 decimal precision. So 120 square root of 125, which is 11.2 miles. So we have 11.2 miles to get to oil rig to refinery. And now all of that is underwater. So cost of the blue path is 11.2 miles times $500,000 so that's $5.6 million. So you see that it's $600,000 more, right? To go to the closest path, because the cost for the underwater, right? You have to go to depth, you have to weld under the, right? It's a lot of headache to put these pipes underwater. So of course they're going to cost more. And when they cost more, you see that the blue path, even though it's much shorter than the black path, it actually costs us more to put those pipes. Have we used calculus? No. So is there something else that we can try so we can actually use calculus and maybe get better result? Sure. How about we go with the red path for some distance, some unknown distance x, up the shore, and then cut through the water with some unknown distance d. So I don't know x, I don't know d, but for sure I would love for this to be the minimum cost, right? So I am going to minimize cost equation and see what I get. But before I do that, I need to, well, let's write, I can't write the cost equation because I don't have x and a d yet. Can I write either one of these Well, actually, I can write a cost equation, what I'm talking about. I can. Number 3, cost is equal to 250,000 times x plus 500,000 times d. And I want that to be minimum. So this is my cost equation. This is what I want to achieve. And remember what I am right now. Right now, I am a consultant, independent consultant, who is not, I have nothing with a company that is drilling. I have nothing to the company that is working on oil, nothing, right? I'm just independent contractor, consultant who is going to bid for the pipeline as well. So an engineer is now computing the minimum cost for the pipeline. And if I come up with a number smaller than 5 million, guess who's winning the bid and who's going to, yes, make the money? Because the two other companies said, the black company said, we are going to use the smallest amount, like the most expensive pipe for the shortest distance. The other ones are saying we're going for the short, right? They did not consider other situations. I just want to see what the red is going to give me. If I'm not able to beat 5 million, well, tough luck. So now let's take a look at my constraint equation. Is there anything in this geometry that can link x to d? Do you see anything in this geometry that you could actually use?
Let's see, I guess you could say that x and d, the x triangle xdl, that would be an obtuse triangle, right?
Yeah, but we don't have any of the angles, so we can't use that one. XDL is out.
So what if we take 10 minus x, that would be the side of triangle 10 minus x.
Nice. You just solved the problem. 10 minus x, and here's your right triangle. You can use Pythagorean Theorem in the right triangle. It connects x and d, and that's your constraint. So you have 5 miles squared plus 10 minus x squared is equal to d squared. Right? The d, if you look at the picture, d is the hypotenuse, and then 10 minus x and 5 are legs. So 5 squared plus 10 minus x squared, those are legs, is equal to d squared. From here, you solve for d, and you plug that in the upper equation. You hit that with the derivative, and you will calculate x. And then you can calculate d, and you will have the values. So let's go. D is equal to the square root of 25 plus, and now we expand this one, which is 100 minus 20x plus 2x squared. D equals, no, it's just x squared, you're right. D equals x squared minus 20x plus 125. We plug that in the cost equation, which is our objective equation, to get 250,000 x plus 500,000 times the square root of x squared minus 20x plus 125 is equal to a minimum. And at this point in life, you differentiate, because now you have equation with only one variable in it. And when you're done with differentiating this, you will have your equation to solve. So that's 250,000 x, derivative of x is 1, plus 500,000 times, and now you're differentiating square root. If you remember the way to differentiate square root, you put 2 times the same square root in denominator, and then you put its derivative on top, which is 2x minus 20. All of this equal to 0. Now you have your 500,000, and then you factor the 2 and cancel it, so you have x minus 10 divided by the square root of x squared minus 20x plus 125 equals to negative 250 when you move 250,000, right? When you move it to the right, picks up negative sign. And then you divide by 500,000 and multiply by square root. So x minus 10 is negative 1/2 times the square root of x squared minus 20x plus 125. So when you divide 250,000 by 500,000, you get 1/2, and then the square root that was in the denominator gets multiplied. So now you can multiply half to the other side and leave a negative, because when we square it, we'll kill it. So it becomes 2x minus 20 is equal to the negative square root of x squared minus 20x. So this is now basic algebra when we are just trying to solve the radical equation. So we square both sides to kill the root, and it will also kill the negative at the same time. We get 4x squared minus 2 times 20 times 2, that's 80, x plus 400 is equal to x squared minus 20x plus 125. The square will kill the negative, and it will kill the square root as well. And now we need to combine all of this to one side, so we have 3x squared minus 60x and then plus 275 equals 0. Now it's not divisible by 3. 275 is not divisible by 3 because it adds to 14. So we're just going to use software quickly to solve this, because we can't factor it. I'll use Mathematica. Solve. Three x squared minus 60x plus 275 equals 0. And we will get x equals 7.1 miles as the length to go up. Now, once I have 7.1 miles going up, I can use my d equation. D equals square root of x squared minus 20x plus 125 to calculate d. That's going to be 7.1 squared minus 20 times 7.1 plus 125. So we can calculate this really quick. So square root of 7.1 squared and I have 5.8 miles underwater. So now So this is ground, and this is water under sea. Sea. Whatever. So what's the cost? The cost of the red path is going to be 250,000 times 7.1 plus 500,000 times 5.8. So I have 7.1 times a quarter plus 5.8 times a half. It gives me 4,675,000 on the cost. So if you take a look at the cost, this is different than the 5 million tag. Save 325,000 savings by doing this calculation. So what is for this company to give you 50 for your troubles, which literally took 15 minutes. 50K for 15 minutes, I think it's a good deal.
Wow.
And, right? They still save $250,000 by paying you 50K for a 15-minute calculation. I think it's a good. But the trick is that you have to come up with a report, and that's where your project comes in. Because if that looks like crap, guess who's not considered? You, right? Now, do they want to see your calculations? No, they don't care. They want to know what are your methods, right? They want to know how you're saving them money. If they understood the calculations, they wouldn't be hiring you, right? Remember, the richest people, they don't go to school. They don't have time for that. They make money. And that's why they have money. So they don't know how to calculate any of this stuff. That's why they give you the 50,000, right? So you can do these little calculations. And then they're going to make millions and billions upon that, right? It's a very simple mechanic of how it goes, right? And then everyone is happy, I guess. So if you go and you put all of this in your paper, I have no clue what the hell is going on. They like to read words, right? They want to see that they are assured that this is the cheapest possible way. So there's going to be a chart. If you use the black path, you are going to pay $5 million. If you use the blue path, which looks like it's the best one, you're going to pay more than $5 million. And if you use the red path, the one that I calculated, right, you're going to save 300-something thousand. At which point, right, when they pay you out, they're still saving a lot of money. So this is the way you're making money, right, as engineer or consultant or whatever. So this is, I believe, one of my favorite examples, going through all of these calculations, right, where you can clearly see how you can cash in on these things once you graduate. Now we're going to take a break, right? When we come back, we have to linearize and do some differentials. So we'll see you in 5.